Okay, so it's now a great pleasure to introduce our final speaker of the morning session, Pascale Aussillous from Marseille, who's going to talk to us about granular discharge flow from a silo with an outlet situated at the corner. Pascale, thank you so much for accepting our invitation. It is very nice to see you again after such a long time.
Yeah.
And please start your talk. Go ahead.
Thank you very much, Yuri, and thanks a lot for this invitation, which gives me the opportunity to come to Brazil virtually and to meet all of you. So I'm not going to speak about collapse, but I'm going to present some results we have about granular discharge flow from a silo, and more particularly what's happened if the outlet is situated at the corner. So this work was done with a PhD student, Samira Laidaoui, in collaboration with Blanche Dalloz at the lab in Marseille. But it's also the result of the continuation of a lot of work from other PhD students, Mébérica Benjamin, Zhou, Zhou, and a collaboration with Pierre-Yves Lagré, Stéphane Popinet from Sorbonne University, and Pierre Rouillet from ERSN. So you may all know that in silo discharge, the flow rate is constant. And that's why we use sand in our glasses still since the 10th century, because the flow is constant and it's a good thing to measure time. So to explain this behavior, in 1852, Hagen suggests that it exists a free-fall arch. So if you look at this kind of silo, really simple silo, which is just a cylinder with a circular hole at the bottom, you can suppose that there is an arch which is based on this on the size of the bottom. So I will call in this talk, I will call D the size of the outlet. And then if there is this arch, I can just suppose that the particle fall in free fall from this arch, which give a velocity at the outlet which scale with the square root of GD. And then the flow rate is just the velocity times the surface. And we obtain this scaling, which says that the flow rate just vary with the outlet size at the power law 5 half. And this power law works wonderfully. It works really, really well. But it doesn't give what's happening inside the silo. It doesn't give the fine description of what's happening inside the silo. So we get this result from 1852, but the silo discharge is still an open, active subject of research. So recently, a team from Spain by Zhou, so this team developed the same kind of apparatus that was shown before, monolayer apparatus. And from this monolayer apparatus, they measure what's happening at the outlet. So they get the velocity, they get the density. It's really interesting to have the density in this kind of experiment. And what they found is that if you plot the velocity versus the size for different outlet size, all the flow is self-similar. That means that if you divide the horizontal position using the radius, and then if you divide the velocity using the maximum velocity, you find that all the data collapse. That means that the flow is self-similar. And that's really, really nice, because if the flow is self-similar, that means that when you calculate the flow rate, everything is given simply by what's happened at the center. So if you get the velocity of the grain at the center and the density at the center, you can have the flow rate because it is self-similar. So they measure the velocity at the center, and they found that the velocity scale as the square root of GD, like shown previously by Hagen. But most recently, the same group, they show that if you follow what's happening on the vertical position at the center, because we know now that the center is where we have to look. So if you look the vertical position at the center, you can find that, if you suppose there is a free fall, the acceleration should be this line, an horizontal line. So that's the acceleration versus the vertical position. And they found that doesn't follow a free fall. The acceleration is not g, but there is an acceleration zone situated at the outlet on a typical size, which is the size of the outlet. So it's not exactly what Hagen was saying, but it's the same scaling. And recently, what's really interesting us is that Staron and collaborator using continuum simulations, the one we have seen, the myophile visco-plastic rheology. So using this continuum modeling with Juris or Basilisk with a CFD code, they found that you can reproduce the flow rate of a silo discharge simply using a myophile rheology. That's really interesting us because we wanted to see if we can use this rheology more generally. So what we wanted to see in silo discharge is what's happening if now we are using a non-conventional geometry. So why do we want to do that? Do we want to do that? Is our first motivation from collaboration with IRSN, which is a French institute for research for nuclear safety. So why? What is the relation between silo discharge and nuclear safety? So in fact, if you look inside the power plants, they use fuel rod. And these fuel rods, in fact, are 4 meters long and 1 centimeter diameter. And in this fuel rod, you get the uranium, the fuel, and this fuel is it's fragmented due to the fission reaction. And this institute, they work on hypothetical accident. And what is emerging is that what's happening if the fuel rod would break. And what I wanted to know is what will be the flow rate of the fragment which will go inside the coolant pool to understand how this accident, what will be the consequence of this hypothetical accident. So, and if there is a leak on a rod which is 4 meters long and 1 centimeter diameter, this leak will be on the side. So we were interested to know what is a silo discharge when there is an hole, not at the bottom, but at the side. And more generally, if you think about industrial safety, if you think about a normal silo, because of the shear stress at the wall, if there is an accident, it will be on the side. If there is a leak, it will be on the side. So what the question we ask is, what is the role of the position of the orifice on the discharge flow rate? And the second thing we want to validate is the use of a continuum modeling on this non-conventional geometry. So we did some experiments and we decided to use a rectangular silo. Why a rectangular silo is because we can see what's happening inside, and like in the previous talk, which was really interesting. With this kind of apparatus, we can see what's happening inside thanks to a camera. And we can make a PIV to measure the velocity at the wall. So we use 3 rectangular silos with 3 different positions of the orifice at the bottom, which is our references, at the side and at the corner. And typically the apparatus is 6 or 10 centimeter large, 50 centimeter, the height is 50 centimeter, or for the last experiment, we use a bigger one, which was 1 meter. And which we have a really nice apparatus which are easy to do, and we can change 2 important parameters, which is the size of the orifice, that will not D, and we can change the thickness of the silo, and that's an important parameter. We change it from 3 to 40 millimeters. We use spherical monodisperse beads, either glass bead or ceramic bead, and we also vary. The size of the particle between 100 micron and 4 millimeter, but in this talk, I will only speak about what's happened for small particle because I don't want to speak about side effects that are really interesting, but today I will focus on what happened for small particle without any side effect. So here you can see a typical movie with an outlet at the lateral side. So it's just a silo discharge, but you can see what's happened if the outlet is not at the bottom. Thanks to an electronic scale, we measure the rate over time and then the flow rate, which is on all these experiments, the flow rate is constant. We have a steady flow. And so first, let's begin by the simplest experiment, which is a rectangular silo with a bottom orifice. So in this graph, I plot the flow rate versus the size of the orifice for two different thickness, a thin silo, 3 mm, and a larger silo, 10 mm. And what we can see is that for both experiments, we recover a power law, which is 3/2. And this power law, it's exactly the scaling that we can suppose using eigen scaling. If we have a free-fall arch which scale with d, then the velocity scale with the square root of gd, and the flow rate, no, the surface is d times w, and then we recover this power law 3/2. If we made dimensionless the data using the thickness of the silo, all the data superimposed, and we have this nice scaling 3/2, so nothing special. We decided to use this local rheology of a dry granular medium. So this continuum modeling, I think we already speak several times on this myophyte rheology. So it's a local rheology. We just say that the shear stress is proportional to the normal stress. So it's a frictional rheology, but the friction coefficient depends on this famous I number. I got a movie, I think, to explain this I number, but Laurent did it really well just before. So then this myophyte rheology, mu depends on this parameter I, and we will use the usual myophyte empirical laws that most of people are using. And in this local rheology, you also have this phi-phi relationship, but in this experiment, which corresponds to dry granular flow, we will use Basilisk, which is a solver, we just solve Navier-Stokes equation, in fact, and then we use an incompressible code. So we won't consider the role of the volume fraction in this talk. So what's happened is that to use this equation, we did like previous talk, we define an effective viscosity. And this effective viscosity is here. This is given by the friction times the pressure divided by the shear weight. We also use a regularization technique. So we just solve the mass conservation and momentum conservation. So with this simulation, we can, here with the no-slip condition, you can see a silo discharge, which is, there is nothing special on this silo discharge, that's the velocity field. So we recover that the particles are accelerating in a zone really close to the outlet, on the typical scale, which is the size of the outlet. And if we calculate the flow rate versus the size of the orifice, we recover the eigenlaw. So what now is really interesting with this continuum simulation is that it gives us some insight of what's happening inside the silo. So if we look at the pressure field and the velocity field, we can see, we can measure at the central streamline in the middle here. We can measure the velocity, the vertical velocity versus the position here, the vertical position. And so we can see, so this is, everything is normalized using the size of the orifice. So you can see that the velocity is constant. So we have a dense granular flow with a constant velocity in the upper zone. And close to the orifice, the velocity increase. We have an accelerating zone, which is which scale typically with d. And for the pressure, we have a constant pressure in red here at the top of the silo, and then the pressure decrease, and the pressure go to 0 at the outlet. It go to 0 because there is no going below. So that means that if we look to the Navier-Stokes equation close to the outlet, what we can see is that if the pressure go to 0, the effective viscosity go to 0. That means that all the terms which come from the granular rheology vanish, and we just obtain that close to the in the outlet area, there is just a balance between the acceleration and the gravity, which gives the famous eigenscaling. If we go in the upper layer at the top of the silo, we can see that now the pressure is constant, the velocity doesn't depend on the horizontal position, and then all the terms which depend on Z vanish, and then we just found that there is an equilibrium between the friction and the gravity, which is similar to Janssen effects, and which can give the scale of the velocity and the scale of the pressure. So this rheology, it's really nice because it gives us some insight of what's happening inside the silo. So that was for bottom orifice. What's happened if we now consider a lateral orifice? So the experiment, on the experiment, we put the lateral orifice not close to the bottom, but a little bit higher, so we have a particle below. And then we vary the size of the orifice for several thickness of the silo W. So in this plot, I just plot the flow rate versus the size of the orifice. In orange, it corresponds to the large silo, 20 centimeters, which is large compared to the particle size. And we recover the eigenscaling with a power law 3/2. But now, if we consider a thin silo, which is 5 millimeters, it was really surprising because we observed that the flow rate is now linear with the outlet size D, and that's a new regime. So if the flow rate is linear with D, if you do a dimensional analysis, you obtain that the flow rate vary with the power law 3/2 with W, the silo slackness, and then that means that the velocity scale with the square root of W. And that's really surprising because in fact, when you have a bottom orifice, no, that's surprising because we don't expect an arch to develop in the thickness because we have smooth surface. We have smooth surface, and I didn't say it before, but you can see it on the sketch. The outlet span the wall thickness. So that means there is nowhere for an arch to develop in the thickness. So it was really surprising to have a velocity which scale with the thickness. So to understand this behavior, so here it's just when we scale the experiment using W, the thickness, you can see that we use a lot of different silos. The thickness vary between 3 millimeters and 40 millimeters. And when we normalize this equation, we can see that when we normalize the flow rate and the size, the aperture, so we plot the ratio between D and W, you can see that all the data collapse, and we have these two regimes. The first one, which corresponds to the Hagen-Bevel regime for large silo, and the second one, which corresponds to this new regime. So to understand this new regime, we can have a look at the velocity field and at the streamline. You can see that there is a dead zone. Huh? You can see, I think you have seen in the first movie, but we have a dead zone which is opposite to the outlet. And you can see that the velocity increase in the zone, which is still linked with D, the size of the aperture. But what is really interesting is that the dead zone increase a lot when the silo thickness decrease. So the thinner the silo, the bigger this dead zone. And what we see is that in this streamline is that the flow is more and more vertical when the silo is really thin. For large silo, you have a curvature, but for thin silo, it seems to be really, really vertical. And that seems to be a signature of an effect of the friction in the front and rear wall. So is it a side effect? Is it a confinement effect? So is it the friction of the wall which is responsible for this new regime? So to check that, we use, again, the continuum simulation. And this continuum simulation, we did it in 2D. And it is a kind of Eléchaud spirit, or it's a depth integrated or thickness integrated equation, in fact. So the friction on the front and rear wall, we write it as a volumic force, which is integrated in the thickness. So that means it's divided by the thickness of the silo, and this force is a friction force. So it's proportional to the friction, coefficient of friction, the pressure, and it depends on the orientation of the flow. So we solved this using a basilisk, and interestingly, we found both regimes. We found for large silo here, when W is large, we are here on this part of the graph. When W is large, we found the Hagen-Beverley regime. And when the silo is thin, we go to this regime. We don't completely reach this regime, but we quit the Hagen-Beverley regime and we go toward this new regime where the velocity seems to be to scale with the square root of GW. And then we can a little bit understand what's happening inside this configuration, because this friction force is proportional to the orientation of the streamline. And that means that if you look at the equation, the Navier-Stokes equation, if this force is the silo is thin, this force is important. And if this force is important, it can be the most important force and counterbalance the gravity. That's why the higher, the thinner the silo, the more vertical seems to be the streamline. So to understand what's happening more precisely, we use the flow property, we use the high-speed camera. And we compare experiment and continuum simulation. So I can show you a movie from the continuum simulation and a movie from the experiment. You can see that on this experiment, we have plotted the streamline, the flow is really vertical, and we have this large dead zone here. And what we measure first is that we check that in this configuration, again, the flow is self-similar. So if the flow is self-similar, we can just use what we see, at the center of the outlet, and the information which we have in the center of the outlet will give us the flow rate. The flow rate is proportional to the outlet surface and the velocity. Which velocity? The horizontal velocity, so the one which is perpendicular to the outlet. And this horizontal velocity we can separate into two terms: the magnitude of the velocity that we call U0, big U, and the inclination of the central streamline. So if we look at the inclination of the central streamline, we can see that if we plot this inclination versus the aperture aspect ratio, D, the outlet size, versus divided by the stilo thickness, for two W, for two thickness, we can see that the data are superimposed, and effectively, indeed, the inclination of the central streamline depends on the ratio of the aperture. So that means that the effect of the confinement, the effect of the friction at the wall, tend to change the inclination. So the inclination depends on the stilo thickness. And we found the same thing in the experiment and in the continuum simulation for different W. So we propose an empirical law for this variation of the angle of inclination. So the effect of the confinement is on this angle of inclination. If we now turn to the velocity of the outlet, to the magnitude of the velocity, in fact, we recover that it just depends on the size of the outlet D. At the outlet, if there is an arch, it develops only on the size of the orifice and not on the thickness. So the velocity really scales with D. There is a kinetic energy which is transformed the kinetic energy at the outlet depend only on the size of the orifice. So it is an equilibrium between kinetic energy and gravity, potential energy, which give always the same scaling, the velocity scale with the square root of GD. So in fact, on this configuration, using a lateral orifice, we found that the flow orientation is completely controlled by the confinement, but the kinetic energy depends only on the size of the orifice. That's why we found, so we have an empirical law for the flow rate. So in fact, it's not the velocity which scales with W, but it is the angle of inclination. So this empirical law really well adjust, but it's empirical, so it really well adjust our data. We can also understand why there is no effect of the confinement when we are at the bottom. When we are at the bottom, in fact, the central streamline is completely vertical. So there is the effect of the confinement is to change the flow orientation to be more and more vertical. Here, it's already completely vertical. So there is no effect of the side, there is no side effect from a bottom orifice, but in fact, it's just because there is no effect on the orientation. So now we were interested in another configuration because we know that there is a side effect when we are on the lateral side. There is no side effect when we are at the bottom. So what's happened now if we consider a discharge flow from a corner when you have at the same time a flow at the bottom and on the lateral side. So here you can see a typical movie. So what we vary on this experiment, we vary, in fact, the size, the lateral, the horizontal extent of the outlet, dx, the vertical extent of the outlet, dy. So that change d, and we can also change the thickness of the silo. And the question we ask is, can we predict the flow rate in this configuration, which go from bottom to lateral? So here I show you all the data, where we change here it's really all the data. We change dx and dy, and I plot the flow rate dimensioned by the thickness of silo versus the aspiration of the aperture. And here we change the dy, which is the size of the vertical extent of the aperture. When it is equal to 0, that means that we have a bottom orifice. And when we have a bottom orifice, we found the scaling law, the eigenscaling law with the power law 3/2. When we have a large divide, that means that we are really close to, no, that's the last data here. We are really close to, we are at the lateral orifice, and when we are at the lateral orifice, we found that the flow rate can be scaled by a linear fit, which correspond to the lateral orifice that we found just before. And all the data lie in between these two graphs, these two curves. So that means that if we want to predict the flow rate, it seems to depend on all the three parameters, dx, dy, and w. So to be able to predict the flow rate, we perform particle image velocimetry to look at the flow properties. If we look at the central streamline here, we have the streamline, and here we have the velocity field. If we look at the velocity field, we find again that the velocity is small everywhere, except close to the orifice, on the arch, which seems to go from one side to the other one. We verify that the flow is nearly self-similar. So there is more non-similarity, but it's really small, and it's not a first order effect. So it's really similar, and so we will just use the normal velocity at the center of the outlet to get the flow rate. So if we plot the flow rate, so if we plot the orientation of the central streamline here, so in this graph I try to define all the parameters. So we have the outlet size d, we have the normal velocity u perpendicular, and we have the velocity of the streamline, which is this one in green, and we have an inclination in between these two velocity. So if we want to compute the flow rate, we can separate the normal velocity using the magnitude of the velocity times the orientation of the central streamline. And if we plot the orientation of the central streamline versus the orientation of the outlet, we found that we have a linear variation. So here it's all the experiment, and we found a linear variation. Here we use a large silo, so we don't have a strong effect of the confinement, and we found a linear variation. That means that the central streamline is completely given. The orientation of the central streamline is completely controlled by the orifice inclination. So we can write a linear empirical relation. And so this inclination go to 0 for bottom orifice to the inclination given by the previous law for lateral orifice. And this inclination for lateral orifice depends on the thickness of the silo. So now, if we look at the velocity, we found more or less a square root velocity. If we plot the velocity versus the aperture size, d, we found more or less a square root velocity, but it's not completely satisfactory because we see that, in fact, the lateral orifice go really much slowly than the bottom orifice. The flow is much slower when you have a lateral orifice than a bottom orifice. And so this is not so bad, but it's not completely satisfactory. To understand that it depends on this position of the orifice, we can draw this sketch, and we can see that the minimum size that the flow encounter is not at the outlet, but it's just above the outlet because of the orientation of the streamline. So due to the orientation of the flow, the minimum size, the minimum shear is not at the outlet, but it's just above on this length, L, which depend on the size of the orifice, but also of the orientation of the central streamline. And then if you use this length as a typical length instead of D, and what's also interesting in this position in green is that the velocity is perpendicular to this position. That means that the flow rate is given by this section times the velocity. So if we use this length, we found that all the data collapse for the velocity. If we plot the velocity versus this length. And okay, it's supposed to be a square root. In fact, here we have a small particle effect, but I don't want to talk about the particle effect in this talk. So you will believe me, it's particle effect, particle size effect, but the main spelling, it's a square root. So that means that the velocity depends on the square root of the size of the particle, of the outlet, sorry, times the orientation power 3. So using this, we have all the empirical law which allow us to. So now we have an empirical law for the flow rate at the corner, which depend on the thickness of the silo, which depend on the size of the orifice, and we can plot this in this graph. This corresponds to all the dashed line, and you can see that the agreement is quite good. So that means, to conclude, that means that for a silo discharge, we have seen that there is a confinement effect as soon as the orifice is not at the bottom. The streamline inclination depends on the outlet inclination, and this is a competition between the wall friction and the gravity. And the velocity of the outlet is given by this length, which is not aperture, but the length where the shear is maximum, which is compatible with a continuum view point of view. And we have validated the continuous approach on the lateral orifice. And now for future work, we are interested in discharge flow around an obstacle, because we think that it is equivalent to have two corners. And we want to see if we can use the model we have done to understand this configuration, which is used industrially to avoid jamming. Thank you for your attention.
Thank you, Pascale, for a very nice talk. We have time for some questions. Laurent, please, go ahead.
Merci beaucoup pour ce talk. Sorry, it's going to be a very naive question because I don't know much about this configuration. So it's just, according to the scaling law of the discharge, where you have this velocity as a square root of d appearing somewhere, gd appearing, from the experiment, it seems that basically it's imposed by the arch, so basically particular falling over a length which is d. But then in the numerical simulation, you cannot capture that. So where the scale d comes from, because then it's not either a Jensen effect, otherwise we would have the length, the size. So do you have a flow which is basically channelized on a column of larger d or something like that?
You can see on this movie that you have an arch. In fact, you have the velocity is accelerating in the zone which is related to d.
And how can we capture arch with a okay?
No, you don't capture. I mean, it's not this view of arch is a discrete view. So you don't need an arch in a continuum simulation. You don't need an arch, but this arch, this size d is a typical size on which because the pressure is 0 at the outlet, the friction is negligible at the outlet, and the friction becomes important
on length scale of d
size, which is d.
Okay. I see. So you recover the same scaling, but on a slightly different mechanisms. That's right.
But the mechanism is a good one. The mechanism is that the acceleration is balanced.
I see.
Because the friction is negligible at the outlet.
Yeah, it's basically that the size of orifice give you a length scale around which basically things are varying. Okay, I see.
But in fact, we see arch in the simulation.
I see.
The flow gives some arch.
But I think the pressure is flipped, is the other way around, right? In an arch, we see an excess pressure on the grains, and here your pressure is decreasing.
Yeah, so it's not at all a Johnson effect. It's not at all. The Johnson effect is at the top of the silo.
Yeah, sure. Okay, all right. Thank you.
Thank you, Laurent. Do we have more questions? Albans, go ahead. Yes.
Yes, another naive question. Merci beaucoup, Pascal. I see that in your simulations that I don't know if it only is the picture, but there is a thickness in the wall, and in the experiment, I don't see any kind of thickness. The thickness have any role in the simulations?
So it depends on which simulation. On the bottom, we didn't put any.
In the lateral one, sorry.
But in the lateral, we put a thickness. In these forces. We add a forces which is linked to the friction at the front and rear wall, and it is this integrated equation. So that way, these forces depend on W. So the thickness is really, really important on this experiment, on the simulation also.
Oh, no, but I'm talking about the thickness of the wall.
Oh no, okay, you're right. Sorry, we lost. No, the thickness of the wall doesn't play any role. And we put in the experiment, we put some. We don't want the thickness of the wall to play a role, so we put something like that. Like we put I don't know what to call that, but we cut a little bit the wall, so it doesn't play any role.
Okay. Thank you.
Any further questions? I have a quick question, Pascal, from the numerical implementation of Basilisk. So which boundary conditions have you imposed on the lateral walls?
So we have tried both. We have tried slip and no slip. And so none of them is a reality, but we have the same scaling.
Irrespective of the boundary conditions.
Yeah, so we have the same scaling, which doesn't depend on the conditions. The velocity it's a little bit different, but the scaling stays the same.
I see. All right. Okay. Very good.
There's another question.
Go ahead, Albans. Yes.
No, Felipe has a question.
I have a question, but I raised my hand with.
Oh, I didn't see you, Felipe. I'm sorry. Go ahead.
I'm sorry. Yeah, no worries. Thanks for the talk. Well, here you are considering the continuum flow regime. that is normally also considered in the orifice when they are at the bottom of the silo. But I was wondering if, is there a limit, as in the case of the bottom of the silo, is there a limit for the size of W and D to have a continuum flow, or you are always here for a large value of W compared to the grain size, right? So
yeah,
what
but
happens
we have also studied the role of the grain size. And so we didn't go toward jamming because there is this jamming is not described at all by continuous simulation and modeling. So jamming will be the limit of the continuum modeling.
I was wondering if there were this limit that is close to the 5 times the grain size, not that is normally considered for.
But when we go to a bigger particle size, we found that there is an effect of the particle size, and we follow the work of the Zhou group in Spain, and we think that this effect is can be modeled in a continuum modeling using the volume fraction. So we think that there is a dilatation at the orifice, which is linked to the volume fraction. So the volume fraction contains the effect of the size of the particle. But we cannot model it using basilisk because basilisk is incompressible.
Yeah, incompressible, yeah.
Yeah, so I think if we want to model that, we have to go to compressible model. But I think it is on the mu of I and phi of I rheology.
Yeah.
I think it's still on research, but I think that.
Okay, thank you.
Very good. So do we have any further questions? I don't see any hand raised. Pascale, thank you so much for a talk. Very nice. And thank you all the speakers for very nice talks this morning. We have now a roughly 1 hour break, so 50 minutes break. We will be back at 2 p.m. Brasilia time, okay? So in precisely 50 minutes, 48 minutes time for our afternoon session. Thank you very much. Bye-bye.
Thank you.
Thank you, Pascale. Thank you, Albans. Genchao, Felipe, Miguel, and Laurent. Bye-bye.